All right, guys, it's time for some fun with math. And so today, what do we have? We are going to do the review for exam 2 on applications of integrals here. And so remember, on the applications, we were using this method of increments. It gives us the power to build formulas when learned properly. So we're going to use the method of increments here to find the area, the volume, the length, or surface area of each figure below. So let's just kind of go through these real quick. And so to find the area of this figure, remember that's called the length, and this is our delta y here. So a small change in the area will be given by this length times delta y. Whereas if your small little increment is along the horizontal here, we call it delta x, and then we call this the height. And so then our small change in the area, which of course, is this guy right here, is given to us by h times delta x. And then we move on to volume of a disk. So how do we find the volume of a disk? I just said over here we should write, we're trying to find the area of sort of rectangles. We have two rectangles, a horizontal and a vertical. And then over here, let's write, how do we find the volume of a disk? So volume of disks. And so you kind of have a horizontal disk here with delta y, and then you have an r right there. And so to find the small change in volume, it's just pi r squared, which gives us this area right here. And then we just multiply it by delta y, and that shoots it through this height basically to get the volume of the disk. And then over here, we have a small change in the horizontal, so we call that delta x. And then we call this r. And so our small change in the volume is given by this pi r squared again, which gives you the area of that circle right there. And then when you multiply it by delta x, it gives you the volume. And then in the next picture, we want to find the volumes of these washers. And so how the heck do you find volumes of washers? Well, you have two radii here. You have a Rn, and you have this guy right here, which we call R out. And then you have this little small vertical distance here, which we call delta y. And so a small change in the volume is equal to, and then remember the idea behind this, it's just take the volume of the outside disk and take away the volume of the inside disk. So you can write this as pi r out squared times delta y, that's the volume of the outside disk, and then minus pi r in squared times delta y, and that's the volume of the inside disk. A lot of times we'll just write this down as being pi times, and we'll write r out squared minus r in squared, and we'll pull the delta y out on the right. And then over here, when you have this vertical washer, you have a small change in the horizontal here, which we call delta x. And then again, this little radius is r in, and the bigger radius right here is r out. And so our delta v will be equal to, and we just take the volume of the outside disk, so pi r out quantity squared, we say it just squared, and then delta x, so there's the volume of the outside, minus the volume of the inside, so r in squared delta x. And again, you can take out that pi on the left if you want to, right? R out squared minus r in squared, and take that delta x out on the right. And then finally, to find a small change in the volume of a cylindrical shell, what can we do? And so the idea behind this is you have a small radius right here, and maybe we'll color this in red. And so what you're going to do to find a small change in the volume is you're going to take 2 pi r, which is just the circumference of this little piece right here. And then we're going to multiply it by h, which gives us a surface area, basically right here. So we multiply it by h, we get a surface area. And then we're going to multiply this by a small change here, which is delta x. And that gives us a small change in the volume. You kind of trace it around if you want to. And that gives us a little small change in the volume. And you can actually do this horizontally or you can do it vertically too. And then the next picture, we're going to do arc length. And so how do we find the formula for arc length? Well, it's a small change in this capital L. And so how do you find a small change in capital L? You just remember this is a small change in the x, this is a small change in the y. And so Pythagorean theorem would tell us the small change in the arc length will be equal to the square root of delta x squared plus delta y squared. And then we can choose which one of these guys we want to factor out. Typically, we factor out the delta x. So when you do that, remember what happens. You get 1 plus, and you get this delta y over delta x quantity squared. And when you pull out the delta x squared, the square root just gives you back a delta x there. And then finally, kind of cut this picture a little bit short here, but this one over here, we want to find a small change in the surface area. And so to find that, so to find this sort of delta S, what do we do? Well, right here is our delta L, and this is our radius R. And so we find the circumference right here of that circle, and so that's 2 pi R. And then we just multiply it by this delta L, and that's going to give us this little surface area. And so we multiply by delta L, and that gives us a surface area. And then if we want, we can plug in for delta L, because remember delta L is the same thing back here. It's just the square root of delta x squared plus delta y squared. And then again, you can choose which one you want to factor out depending on the problem. So that's a nice little review of using these increments to find area, volume, arc length, and surface area. So now let's do some problems. All right, so let's come down here. We got a bunch of problems. So the first thing I want to point out is that we are going to use the region in the first quadrant bounded by y equals x squared and y equals 4 to answer all the following problems. But for each one, we're going to make sure we draw a picture and use the method of increments. So let's come over here and let's draw this picture here. So we want it in the first quadrant. So I only need to worry about this first quadrant right here. So here's my x and here's my y. We have this y equals x squared, which just looks like a u on that side. So that's that y equals x squared. And then y equals 4 is just a horizontal line right here, y equals 4. And so in this one, we're trying to find basically the area of this region. And we're going to do it two ways. We're going to do it first with respect to x, and then we'll do it with respect to y. All right, so if we're going to do it with respect to x first, the idea is you take this vertical rectangle right here. So here's my little vertical rectangle. And I want to find a small change in this area here. And so how do I do that? Well, I set up my little increment, small change in area equals, and this, of course, is my delta x, and this is my height h. And so it's just going to be h times delta x, which equals, well, how do you find h? So h is just this height. Let's use a different color. It's just this height up here minus this height down here. So that's just 4 minus x squared. So this will be 4 minus x squared delta x. And so then my a will be equal to the integral, and I'm going to start here at 0 and then go to this intersection point. So I guess I need to find that intersection point. So when is x squared, because there's the height of the function, equal to 4? And so take the square root of both sides, so it's equal to plus or minus root 4, which is equal to plus or minus 2. And of course, we like the positive part, so it just goes to 2 here. And you can see the height is 4, right? So that's easy to see. And we're going to go for the integral from 0 to 2 because we're going from left to right. And we have 4 minus x squared dx, which now we can integrate. So we integrate 4, so it's just 4x because the derivative of 4x is 4, minus, and we just add 1 to the power and divide by, and we're going to go from 0 to 2. And so that's going to be equal to then, we're going to plug in this upper limit. So 4 times 2 minus 2 cubed over 3, and then take off, put that in parentheses, when you plug in 0. So when you plug in 0, you just get 0. And so that's going to be equal to 8 minus 8/3, which of course is equal to 24 over 3 minus 8 over 3, which equals 16 over 3. And don't forget the units since it's area, it must be units squared. And if we want to, we could check that with a calculator, but I know the right answer, and that's the right answer. All right, so that looks good. So that was with respect to x. So with respect to x. Now, let's switch gears and do the same thing, but let's do it with respect to y. And so how do you do it with respect to y? Well, we're just going to draw the same picture here. And so our picture, we might as well get used to this because we're going to draw this picture on every single one. It's just y equals x squared. So there's my x-axis and my y-axis. And then I just have this y equals 4. And I'm trying to find that area, which I now know is 16 over 3 units squared. But with respect to y, I'm going to do this little horizontal rectangle. And so to find my delta A now, what does it look like? Well, I have my little delta y here. And then here I have this length, L. So it's going to be L times delta y. And how do you find L? We just take the right-hand side of the graph and subtract off the left-hand side, and that tells you what L is. So it's going to be equal to something minus something, delta y. And so up here to find out y is, we're going to have to solve that for x. And so that's x equals, and that's plus or minus the square root of y, but we're on the positive side, so it's square root of y. And then this one right here, oh, that's an easy one. That's just 0. Right? So that's just x equals 0 right there. And so it's going to be square root of y minus 0. And so my a, when I integrate this, it's going to be the integral from 0 to, and I have to find this point again. And so it's going to go up here to 4. So we're going to go from 0 to 4. So 0 to 4 of, and we'll write this as y to the 1/2, and then minus 0 is just 0. And then that's dy. And so now let's see what the integral is. And so now we're going to add 1 to the exponent and divide by it. And so let's go nice and slow. There's no reason to go fast here. So add 1 and divide by it. And then we're going from 0 to 4. And so that's going to be equal to, it's going to be equal to y to the 3/2 divided by 3/2 from 0 to 4, which is really a 2/3. We multiply by the reciprocal basically. And then y to the 3/2 is a y root y from 0 to 4. So remember, y to the 3/2 is really what? It's really the square root of y cubed. And then don't forget, you can simplify that because that's y squared times y. And radicals go through multiplication. So it's really y root y. The square root of y squared is just that first y there. All right, so let's start plugging in. So we're going to get 2/3. All times, we'll plug in 4. We get 4 root 4 minus, and then we'll plug in 0. So that's just 0. And so that's going to be equal to 2/3. And then 4 root 4, what is that? That's 4 times 2, because root 4 is 2. And so that's equal to 8 times 2, which is 16 over 3. Oop, yep, that's exactly what we thought it was. And then don't forget it's units squared. All right, so you can do this with respect to x, or you can do it with respect to y. We're practicing both ways, just so we can, prove that we can do it both ways. And usually one way is easier than the other, although in this case, I think they might both be of the same difficulty since you have to deal with a fractional exponent when you do y. I don't think one's better than the other in this particular case. All right, so let's move on to finding volumes. And so we're going to do, discs, washers, cylindrical shells. Those were the 3 methods that we had. And so how do we do these? First, for discs, let's draw the picture. All right, so here's our picture again. We're just using the same graph every single time. So here's our x, here's our y, and here's our y equals x squared. So y equals x squared. And here's our y equals 4. And so what we're going to do is we're going to revolve this around, it says the y-axis. So we're going to find the volume of revolution if the region, and remember what the region is, this is the region enclosed by these graphs in the first quadrant, is revolved around the y-axis. And to see what's happening here, we can just grab this little guy right here and revolve it around. So we just take a little rectangle and we revolve it around the y-axis. And you should get something that looks like a disc, basically. And so there's our disc. It looks a little bad over here. Let's make it a little better. So there's our disc right there. The disk has a radius r, and notice it has a small change in the sort of vertical, so that's our delta y. And so our delta v here will be equal to pi r squared. That gives us this area of this disk right here, and then we're going to multiply it by delta y to get the volume. And so that's going to be equal to, so we have to find this radius right here, r, and so that radius r basically falls on this graph, which is y equals x squared, but our r is actually equal to this x value, and so this tells us that x is equal to, it's the square root of plus or minus y, but we care about the positive part, so x equals square root of y. And so pi is equal to, if you wanted to, you could just write x here. But notice then you have delta y to compete with. And so you got to change this x into y stuff. So x is really root y. So it's pi square root of y squared delta y, which of course is just equal to pi times y delta y. And so my volume V is equal to the integral. And now this one, since it's horizontal, it's going from the bottom to the top. So let's give these numbers. So the bottom here is 0. And of course, the top here is 4 because you have y equals 4. So it's going to be the integral from 0 to 4 of what? Pi times y dy. And then be careful on the problems because some problems might just say set this up. This problem doesn't say that, but on the exam, a lot of times I'll tell you guys just to set it up. And so if it says just set it up, you're done. But of course, this integral is so easy, I have you guys do it because it's just equal to pi and you integrate. So y squared over 2 from 0 to 4 is equal to pi over 2 times you plug in the upper limit. So it's 4 squared minus plug in the lower limit, 0 squared. And so it's basically 16 over 2 pi. So that's what, 8 pi. And then don't forget, it's units, it's volume, so units cubed. And so that's how you find the volume when you revolve this around the y axis. All right, so let's move on to the next method here. So the method of washers. And so for washers, what do we have? I have an x and I have a y, and I have to make my graph here. So here's my graph, y equals x squared. And then I'm coming across here, and so that's y equals 4. And I'm revolving it now, it says across the x-axis, so it's going to go around here. And so what does that look like? So it comes up and down like this. And to revolve it around the x-axis, I just do the outside first and then the inside. And so kind of just draw it around here like this. So there's the outside disk right there. And then the inside disk is right here. So then I'll revolve it, the inside piece around. I like to put a little inside. And so then you can see the disk. It's not drawn to scale, of course. But I can see the little pieces here. So, up here, I see this is my delta x. And then I have my R in and R out. So, right here is my R in. And then my R out is all the way up there. So there's my R out. And to find delta V, a small change in the volume, I'm going to take this pi R out squared times delta x. That's the volume of the outside disk. And then take off pi times R in squared delta x. That's just the volume of the inside disk. And so that'll be equal to pi times, and it's just R out squared minus this R in squared, then delta x. And so we need to find these. So notice, what's R out here? R out is just the height basically from here up to here. And it's always the same. It's always height 4. So R out is just 4. Whereas R in, it's the height from here right to there on our graph. And so that's just y, and that's just x squared. And so this will be equal to, I guess we can write right here, pi times, and then we write 4 squared minus x squared, quantity squared, and then delta x. And so now I can find my v. My v is the integral from 0, because you start here at 0, And then we have to go right here. So now remember we found that intersection point is just 2 comma 4. And so here that's just 2. And so the integral from 0 to 2 of pi, and then all times 16 minus, and then x squared quantity squared is x to the 4th dx. And so that'll be equal to pi times, and the integral of 16 is 16x, minus the integral of x to the 4th is x to the 5th over 5. And we're going from 0 to 2. And so that'll be equal to, we have pi here, and we're just going to plug in now 2. So we get 16 times 2 minus 2 to the 5th over 5, and then take off when you plug in 0. Now, when you plug in 0, hopefully you guys can see it's just 0. And so that's going to be equal to pi times, and then we have 32 minus, and you got to do 2 times 2 times 2 times 2 times 2. So what is that? 32 over 5. So 32 over 5, which is kind of a pain, but it's not terrible, right? So this one's going to be pi, and we multiply top and bottom by 5 here. So you get 150, 160 minus 32 over 5. So that's going to be equal to 160 minus 32 is 128, maybe over 5 times pi. Good. And then units, don't forget cubed. So that's the volume there. All right, so let's see. Okay, so that finishes off the method of washers. And now let's go on to my favorite methods here, cylindrical shells. And so down here at the bottom, we have our cylindrical shells. So now we want to find the volume of revolution if we revolve around x equals 3, which is always an interesting problem. So let's go over here, and we have x, and we have y, and we just redraw. We're doing the same region every single time. So here's my y equals x squared, and here's my y equals 4. And so I want to take this region right here and revolve it around this x equals 3. So let's put x equals 3 right here. And then remember, this little intersection point we found, it's just input 2, output 4. And we want to revolve this around with cylindrical shells. So it's a little tricky to see what we're doing, but the idea is we're going to grab this little rectangle here, and it's a cylindrical shell, so it's this vertical rectangle. If you drew a horizontal rectangle, it actually would be a washer when you revolve it around. And we're going to take it around this guy right here. So I'm going to grab this outside. I always like to do the outside first, because it gives you a little bit better picture. So I grab the outside and I wrap it around. And then I grab the inside here the best I can, and I wrap it around. And hopefully you can kind of see, oh yeah, there's like a cylindrical shell here where you have your delta x up here. And then you have this height h right here. And then on the inside here, it's hard to see, but you have this radius basically right here. There's a radius right here, r. All right. And so what do we need to do? We need to find the volume of this thing. And so a small change in the volume will be equal to, we take the circumference 2 pi r, right, which gives us basically the circumference of this thing, this distance around. We're going to multiply it by h. When you multiply by h, it gives you this little surface area of the cylinder. And then we multiply it by delta x to get the volume. And so then this is going to be equal to, well, it's going to be equal to what? All right, so my r here, it's basically going to vary. So to figure out r, hopefully you can kind of notice here, it kind of comes back here where this is like your x. And so your distance, my little r here, is actually equal to the total distance goes from here to here, which is 3. And then I'm going to take off, and I'm going to take off my, let's color code this. I'm going to take off my x. So that's my radius. It's kind of like you take the whole distance from here to here, which is 3, and you take off your x right there, and it gives you distance in between, which is your r. So this will be 2 pi times 3 minus x. And then the height, well, that's a little tricky too. So you take the top minus the bottom down here. And so my h, the top, is equal to height 4. And then the bottom right here is given off by this height, y, which is x squared. So it's going to be 4 minus x squared. So times 4 minus x squared. And of course, you still have that delta x at the end. And that should do it. And so my v would be equal to the integral from 0. So you're going from 0 here over to right here, which is 2. And notice it's the vertical here that's the vertical that's changing along the x, basically, right? So that vertical rectangle, that's how I know it's with respect to x and not with respect to y, because how it moves, right? If it went like this, that would be moving with the y, but it moves like that, so it's moving with the x. So it's going to go from 0 to 2, and you can also see that because everything's in terms of x. And then it's 2 pi times 3 minus x times a 4 minus x squared, and then my deltas become a d, so dx. And so there's the integral that gives me the volume. And unfortunately, it doesn't say just set it up, so we actually have to find it. And so to find this, I probably would have to, I guess I have to multiply everything out. So it's going to be equal to the integral from 0 to 2 of 2 pi. And let's just multiply this out. So that's going to be a 12. This is then a minus 3x squared, and then a minus 4x, and then a minus would be a plus x cubed, and then all dx. So the good news is you don't have to combine like terms because there are no like terms. And so now we can integrate here. So it'll just be 2 pi, and then we have a 12x minus, and then this next one, when you integrate, when you add one and divide, you just get x cubed. And then minus, when you integrate 4x, you get 2x squared. And this is really just a guess and check. So I'm just kind of guessing and then taking the derivative instead of adding and divide by, but you can add and divide by. But notice if that's your guess, you take the derivative, the 2 comes down, you get 4x, and then plus x to the 4th over 4. And we're evaluating this from 0 to 2. And now we just do what it says. So it's going to be 2 pi all times. And now we're going to plug in this 2 here. So I get 12 times 2 minus 2 cubed. And I'll go kind of slow. So minus 2 times 2 squared plus 2 to the 4th over 4. And then minus, now notice what happens when you plug in 0. Everything is just 0. And so it looks basically like that. And this simplifies pretty quick because the numbers are actually pretty nice. So 12 times 2 is 24, minus 8, and then plus, now 2 to the 4th divided by 4, it's going to cancel with one of those 2 squareds. So I just get plus 4. And so it's going to be equal to 2 pi times, and then 24 minus 8 is what? So that's going to be, I have 16 there, and then minus 8 plus 4. And so that's going to be, what, 8, and then plus 4, that's going to be 12. And so that's going to be equal to 24 pi. And then don't forget units cubed, because you're actually computing a volume on that one. All right, so there we are with the cylindrical shells. All right, so what's next? Number 5. So number 5, we move on to arc length and surface area. So now we want to find the arc length of the parabolic part of the region. Oh, so what's that? And the good news is you can use a calculator to evaluate this integral to 2 decimal places. So we get to use some technology. So let's first figure out what this thing is actually asking us to do. So remember, we have this y equals x squared right here. We have this y equals 4. We do get a region right here, but it's interested in the parabolic part of the region, which is just this piece from here to there, because that's the part of the parabola. It wants to find that arc length. And so remember, that intersection point is 2, 4. And to find that little piece of the arc length, we just take a little piece inside here called delta L. And delta L has a small delta X component on a right triangle and a small delta Y component. And delta L is equal to, remember, by the Pythagorean theorem, delta X squared plus delta Y squared. And so for this one, I'll just take out that delta Y squared. So you'll get the square root of 1 plus delta X over delta Y quantity squared. I'll factor out that, oops, I got that backwards. I'm factoring out the delta, so I can do that in between step if you guys want. Right, so what you're doing here is you're basically taking out this delta X quantity squared, which, you know, we do this little trick a lot. You factor out something, because you want it to wind up to be a certain way. So we factor out that delta x quantity squared, and so you can see that you should have delta y on top and delta x on the bottom, right? So delta y over delta x quantity squared. And then the square root of delta x squared is just a delta x. And so my L is going to equal the integral, and I'm going to go from 0 to 2. I'm doing this with respect to x, so 0 to 2. And it's the square root of 1 plus. And when I go to the integral, all my deltas become d. So dy dx quantity squared. You're a little fast there. So dx quantity squared dx. And so I need to find the derivative. So what's the derivative of y? Well, if y is equal to x squared, the derivative of y, so y prime is just equal to 2x. And so this will be equal to the integral from 0 to 2 of the square root of 1 plus 2x quantity squared dx, which you can simplify a little bit. So the integral from 0 to 2, square root of 1 plus 4x squared. And now we definitely don't want to do that integral, because if you did it, it's probably a trig integral, which would take us a long time to do. So that's why we're allowed to use our calculator. So if you have a calculator, take it out, and we will approximate this to 2 decimal places, it says. So on your calculator, the easiest way to do this is probably just to hit the integral button. So I'm going to turn my calculator on, hit math, and go down to this integrate here. So finite integral right there, and hit enter on it. And then I'll type in 0 to 2. We'll kick it over and type in the square root. So second square root of 1 plus, and then we have 4x squared. And then over here we have a dx. So we got to put an x in there. We hit enter, and we get about 4.65 out. And then don't forget the units. Since this is arc length, it's just units. And so approximately 4.65 units. And so that's the arc length. In fact, maybe we'll put a red box around it, because that's the length of that curve between x equals 0 and 2. All right, so now on to surface area. So now what we're going to do is we're going to find the surface area of revolution by revolving that parabolic part of the region about the x axis, and then we're going to use our calculator again to evaluate this integral to 2 decimal places. So let's just take a look at what this might look like. And so here I have my y equals x squared. And then, here's my y equals 4, which I actually don't need for this problem because I'm just considering this parabolic part. So I don't even care about the y equals 4. And that's between 0 and 2. And we're going to wrap this around the x-axis. And so you have to kind of imagine you just take this piece, I guess it looks like this, and you're just going to wrap it around, and it's going to give you a surface, basically, when you wrap it around the x-axis. And what is that surface going to do when you have basically a small band here? All right, so this is going to be your delta L. And we're going to wrap this around the x-axis, so it's going to kind of look like this and look like that. And it'll have a little band over here. And so here you have this little radius right here, which you call R. And so to find a small change in the surface area, so we're looking for the surface area of that band, how do you do it? Well, you do it like this. You take 2 pi r, and notice I don't memorize these formulas. I try to see how they're built. So that's that length right there. And then we're going to multiply it by this delta L. When you multiply it by delta L, it gives you a surface area. So we multiply it by delta L. And so this is going to be equal to then 2 pi. And then our r is given by this height, which is x squared. And delta L, of course, is just this delta x quantity squared plus delta y quantity squared. And we'll take that delta y out. So this will be equal to 2 pi x squared, the square root of 1 plus, and we'll have delta y over delta x quantity squared, and then it'll be delta x. And so my surface area S is going to be equal to, oops, I drew that S kind of like an integral. So S is going to be equal to an integral, which is actually an elongated S, from 0 to 2 of 2 pi x squared, And then the square root, and those little deltas become d, so dy dx, we're going to need a derivative here, squared dx. And so again, our y is x squared. And so the derivative, y prime, which is really dy dx, is 2x. And so this will be equal to the integral from 0 to 2 of 2 pi x squared, the square root of 1 plus, and then when you square 2x, you get 4x squared, which we've already done, so I'm just going to write it down, dx. We put this into our calculator, and it's going to tell us the answer. So let's go back to our calculator. And in fact, we could probably just use what we had before. If we just hit second enter to pull the last entry, and then we can just insert probably right here. Let's see, second insert, and then just type in 2, and then a pi, and then an x squared, and then hit enter. And there's a surface area, which was to 2 decimal places, 53.23. So 53.23. And then don't forget the units. This is surface area, so it's units squared. All right, we have just 2 more problems left. So let's go over here to finding mass and doing work. All right, so our last 2 problems here. Okay, so what do we have? We want to find the mass of our region if the density is given to us by this e to the x kilograms per meter squared. So let's draw our region again. And so here's my x, here's my y. We have this piece right here, which is y equals x squared. We have this line going across, which is y equals 4. We even know the intersection point here we found a while ago was 2, 4. And we're trying to find the mass of that region bounded by those 2 curves in the first quadrant. And so how do we find that mass? We have to find a small change in the mass. And so to do that, we're just going to take a little piece of area here, and I'm going to go vertical, although you could do horizontal if you wanted to, I guess. Although, the density depends upon this x there. So I guess it would make more sense to go vertical. So how do we find the mass? Well, the density is kilograms per meter squared. So we're going to take that density, delta of x, and multiply it by delta A. So that delta A is just that small change in area right there where you have delta x here and then a height here. And so what is that going to equal? Well, my density is e to the x, and then delta A is just h times delta x. And so that's going to be equal to, we have to figure out our h, and we actually found h before. H is this top height minus this bottom height. So our h is just equal to 4, because that's the top height. It has height 4. And the bottom height just has the height of y, which is x squared, so minus x squared. And so this will be e to the x times a 4 minus x squared, and then we have our delta x there. And so what we need to do now is we need to do this integral. So to find the mass, we'll integrate. We'll add up all these little small m's, these little delta m's here, these are little increments of m. We're going to go from 0 over here to 2. So 0 to 2. And we have this e to the x, and then times this 4 minus x squared, and then delta x becomes dx, sorry. And to integrate this, how are we going to do it? Right, so we have to use one of our techniques of integration, and it's probably not a substitution because I don't see u in its derivative. So this is probably an integration by parts. And so I'm going to let my u be equal to this guy. So u is going to be equal to 4 minus x squared. And then my dv will be what's left over. So I have left over an e to the x dx. And I can find du by simply taking a derivative of this, which is just equal to negative 2x. And I can find v by taking the integral of that. So the integral or antiderivative e to the x is just e to the x. Oh, and don't forget your dx over here. And then this is going to go down and across. And so this integral is going to equal, I have 4 minus x squared times e to the x. And don't forget, it's a definite integral, so we evaluate from 0 to 2. And then minus, and I go across here, and then so it's e to the x times negative 2x. So it's going to be plus the integral from 0 to 2 of 2x e to the x dx. That minus got taken care of by this minus sign right here. So minus minus gave it a plus there. All right, and so I guess I can continue on because I'm going to have to integrate this guy right here. And so I'm going to have to do integration by parts again. So this time I'll let my u be equal to the 2x right here. And then my dv will be what's left over. And so dv is equal to e to the x dx. And so my du, the reason why I chose it to be 2x is because it gets simpler when I take the derivative. So you take derivative 2x, you get 2 dx. And then when you integrate e to the x, you get your v, which again is just e to the x. And so this is going to be equal to then, and we're going to have this 4 minus x squared times e to the x, evaluated from 0 to 2. And then I have plus, and I go down and across. So down and across here, so I'll have this 2x e to the x, evaluated from 0 to 2, and then minus the integral, I go to cross here, so the integral from 0 to 2 of 2 times e to the x dx. And now I can integrate this last one right here. It's one of my types. And so all together, what am I going to have here? I'm going to have 4 minus x squared all times e to the x. And I'll put the limits at the very end here. And I have plus a 2x e to the x. And then minus, and the integral of e to the x is just e to the x. So it's just 2 e to the x, and evaluated from 0 to 2. That looks good. And now if you want, I can simplify this a little bit. And so it looks like they have an e to the x in common. So I'm going to just take that out. So it's e to the x all times 4 minus x squared, and then plus a 2x, and then a minus 2, evaluated from 0 to 2. And so some of this stuff is going to cancel a little bit. So I'm going to get an e to the x, and then the 4 minus 2 is going to be a 2. So 2 minus x squared plus 2x. And that's going from 0 to 2. And so now I guess I'll just plug in. And so I'll plug in my 2. And so I get e squared, and then times 2 minus 2 squared plus 2 times 2. And then minus, plug in your 0, so e to the 0, and then 2 minus 0 squared plus 2 times 0. And so what is that going to be equal to? Well, inside here, what do you have? You have minus 2 squared plus 2 squared, basically. So that's going to cancel. So I just get a 2 times e squared for my first term there. And then minus, and e to the 0 is just 1. And then inside here, that's 0 and that's 0, so they're gone. And so I just get a minus 2. And you can leave it like that if you want. And just don't forget the units, because it's a mass. It's kilograms. Well, that's perfect. Right? So you have 2 e squared minus 2 kilograms. And if you wanted to check your work, because this one is a little bit tricky, so if you wanted to check your work here, you could actually check it simply by just going back up here and plugging that into your calculator. So if you have a calculator, you can plug that in and you'll get out a number, and you just got to make sure that number is the same as that number, and it should be, because it looks like the right answer to me. All right, so that's how we find the mass. And then finally, the last problem we need to do on here is this number 8, which looks like this, which is a work problem. So let's find the work to pump out a bowl full of water if the bowl is made from revolving that parabolic part of the region about the y-axis. And then it tells us what the density of water is, and it tells us what gravity, acceleration due to gravity is. And what's nice about this one, at the very end, we can evaluate it with our calculator, and we'll just round to the nearest whole number. All right, so let's try to figure out what this is asking us to do. So over here, here's my x and y axis. So I got to draw my graph again. So here's my graph right here, y equals x squared. And then inside here, or up top here, there's y equal 4. And it talks about that parabolic region again. So what we're going to do is we're going to take this parabolic region right here. All right, so the parabolic part, and we're going to wrap it around the y-axis. So we're going to wrap this around the y-axis, and it's going to make a bowl, basically, right? So when you take this around here, you're going to get basically a bowl. So we can actually draw the bowl if you want. So we're going to wrap it around. Maybe I'll use my eraser because I kind of drew that funky over there. And we'll wrap it back. And so hopefully you can kind of see like, oh yeah, there's a little bowl if we wrap that parabolic part around. And it's full of water. So it has a bunch of water in it. And what we want to do is we want to basically pump the water out and figure out the work. So remember, work here is equal to just this force times distance idea. And so what we're going to do is we're going to find a small change in work. And to do that, we have to find the small change in the mass. And so we're going to take a little piece over here. So just take a little piece. And if you look at this, it's basically, you're just, oops, I don't want that. What the heck happened there? Hold on. There we go. Okay. So we're going to take a little piece over here. And so that little piece is just kind of like a little, if you want, it's like a little rectangle and wrap it around. It's a little piece of this thing. That's how we got this thing, right? It's just this little piece right here. And it's like a little disc. And so here we're going to make our R and our delta H. And so here's my R from here to here. And we'll make this our little small change in the height. And I want to figure out for the force, it's a small change in the mass times G. And then the distance is the height we lifted out. So I'm going to call this right here the height we lifted out, H. So this one's kind of tricky because it's drawn on the XY axis. And maybe we'll do the H in black. It'll pop a little bit more, right? So this is our height right here, H. So height H. And then to find delta M, how do you do that? Well, I'm going to have to use this number here. So I need to find a volume. So it's going to be a small change in the volume and then times the mass of the, or density of the water, which is 1,000 kilograms per meter cubed, times my G, which is a 9.8, and then times my H here. And so how do we find delta V? Well, it's just the volume of a disk. And so what we'll do is we'll find the area of that top circle, which is just equal to pi r squared. And then when we multiply by delta H, we get that small change in the volume here. And then times 1,000 times 9.8 is 9,800, and then times H. And so what is that equal to? So this is going to be equal to what? So let's write this as 9,800 r squared. And then what do I have left over here? I have an H and a delta H. And so I need to figure out this R right here in terms of my H basically, right? So what is R right there in terms of H? So on the picture, you can kind of see this. My R is given to me by my X value. And so let's see. So R is equal to X right here. And so what do I know? I know that this distance right here is Y, right, going up there. And so R is equal to, it's equal to what? It's equal to X, and I can actually figure that out in terms of Y. So that implies that your X is equal to square root of Y. And so this is square root of Y. And then there's a relationship between H and Y right here. So what's the relationship? It equals height 4. So this is kind of tricky. So 4 is equal to H plus Y. And so my Y is equal to what? 4 minus H. And so that's going to be equal to the square root of 4 minus H. Yeah, that was tricky, right? And so here I have this equal to, right, 9,800. Oh, but what's nice is I'm squaring R. And so when we square R, you get 4 minus H, because if R is equal to this, R squared is equal to just 4 minus H, right? You're squaring the square root. And so you just get 4 minus H. Oh, that's nice. Okay, so not so bad once you plug it in. And so H times my delta H right there. All right. So now what do I have to do? Now I need to find the work. So work is equal to, and so now it's going to be the integral, and I'm doing this with respect to h. So you got to think about what h is. So h is going to start at the top, which is 0, and it's going to go all the way to the bottom, which for h is 4. So we're going to actually go from 0 to 4, and hopefully you guys see this is h equals 0 and h equals 4, not y. Right? So I made up a kind of like a dummy variable in a sense on top of my x and y axis. And so then this is 9,800. And then I have this 4 minus h times h, and then a dh. And then the good news is I do not need a calculator. I don't need to do this by hand. I can use my calculator. So on my calculator, let me approximate this. And so where is my calculator here? My calculator is not open. Ah, okay. Sorry, guys. Give me 1 sec. I got to open up the calculator. I was like looking for it on here. I open it up. All right. So there's my calculator. And so we'll put this into our calculator. It's not too hard to do. You just hit math. And we go down here to the finite integral. And we're going to go from 0 to 4. And then we're just going to type in this 9,800. And then we need an x here. And so I need a 4 minus x, so left parenthesis, 4 minus x. And then in parenthesis, ooh, I missed that parenthesis there. So hold on, maybe that parenthesis in there. So insert left parenthesis. And then outside this guy, we need another x. And then inside here, I need to put a dx. And that should be it. Then we hit enter. And out pops this number. And, ooh, I dropped off a pi. Oh, hopefully you guys probably saw that. So let's go back and fix this. I dropped off a pi up here. So right here, I should have 9,800 and a pi. So there's a pi here, and there's a pi there, which is important because it changes your answer a little bit. So right here, this, we can go back and just put it in there if you want, even though you just multiply that answer by pi, but same thing. But let's put it in here. So second insert, and then I put a pi right there, hit enter, and now I get the right answer. And so to round to the nearest whole number, this would be 328,401 joules. So 328,401 joules. And that's my answer right there. All right. And so that completes the final review for exam 1. So go have some fun with math.